This is Learning Assessment Problem 9.4. The problem-solving strategy here is that of average power in AC circuits. We are asked to determine the total average power absorbed and supplied by each element in the network here. We have two passive elements, a resistor and a capacitor, and two sources, a current source and a voltage source. Let's label some quantities on this circuit to aid our calculations. We'll name the current source I sub s, the voltage source V sub s, and we'll make those phasor quantities. And we'll have a node voltage at the top here. We'll call that voltage V1 with respect to the reference node at the bottom of the circuit. We'll have a current I1 flowing down through the 4 ohm resistor and a current I2 flowing through the capacitor. So we'll begin by determining the node voltage V1. We'll apply Kirchhoff's current law at that node V1, and we'll have V1 divided by 4 ohms for a current minus 12 at an angle of 0 degrees amperes plus V1 minus 4 at an angle of 30 degrees divided by the impedance of the capacitor minus J2 ohms, and this equals 0. Simplifying this expression, we have, or we can convert to polar coordinates across the equation and have, or solving for V1, we have 19.92 at an angle of minus 54.49 degrees volts. The expression which we'll use for calculating the average power in a resistor is P sub R is equal to 1/2 times the magnitude squared of the voltage across the resistor divided by the resistance value. So for the power dissipated in the 4 ohm resistor, we'll have P 4 ohm is equal to 1/2 times the magnitude of this phasor voltage V1 squared divided by 4 ohms, or that power is equal to 49.60 watts. For the other passive element in the circuit, the ideal capacitor, we have that power dissipation on average is equal to 0. And that is because the current and voltage are 90 degrees out of phase in a capacitor, and the averaging process results in a 0 average power dissipation. For the current source, the average power, P sub I sub s, will be equal to a minus 1/2 times the magnitude of the phasor voltage that we determined V1 times the strength of that current source I sub s, the magnitude, and the cosine of the difference between the phase angles of the voltage phasor and the current phasor. The minus sign appears in front of this equation because of the relationship between the current and voltage for the current source. The current is flowing upward out of that source, and the voltage across the source is plus to minus, top to bottom, so the passive sign convention will result in a negative power calculation here. Or the power absorbed by this current source is equal to minus 64.43 watts. The negative sign there indicates that this source is actually supplying power to the circuit. Now we have to determine the power situation with the voltage source. First, we'll solve for the current I2, which is the current flowing into the positive terminal of the V sub s voltage source. I2 is equal to the voltage difference across the capacitor V1 minus the V sub S voltage 4 at an angle of 30 degrees volts divided by the impedance of the capacitor minus J2 ohms. And the calculation for I2 results in a magnitude of 9.969 at an angle of 23.99 degrees amperes. Now we can calculate the power associated with the voltage source. P sub V sub S is equal to 1/2 times the 4 volts of the source times the magnitude of the current, 9.969 amperes, times the cosine of the 30-degree phase shift of the voltage source minus the 23.99 degree phase shift associated with the current I2. This is a plus sign in front of this calculation because the passive sign convention for the relationship between the current I2 and the polarity of the voltage source, plus to minus V sub S, results in a calculation of absorbed power. The calculation results in P sub Vs equals plus 19.83 watts, and that is being absorbed by that source. You can go through and calculate the sum of the various powers which have been calculated here, and that sum should equal 0 if you follow the signs associated with each absorbed or supplied power.